So we're going to talk about correlation now. You know that correlation is a way of describing a relationship between two variables. Now, up until now, you've talked about things like a positive correlation, a negative correlation, or a strong or a weak positive or negative correlation, or even no correlation. And what we're going to do is try and quantify this so that we can be a little bit more specific when we're talking about correlation. And the way we're going to quantify it is something called the product moment correlation coefficient. This is often abbreviated to the PMCC, and it has the letter R. So we're going to use the letter R throughout this, and when we do, we're referring to the product moment correlation coefficients, the PMCC. Now, the PMCC describes a linear correlation. Got to be linear, got to be a straight line. If it's not linear, if it's any kind of curved correlation, then this does not apply. So a linear correlation between two variables, and it takes values between -1 and 1. Now, if you have a PMCC of -1, that means there is a perfect negative linear correlation. So all of your data points would lie exactly on your regression line. So an R of -1 would look something like that. If you had a value of R as 1, it would mean a perfect positive correlation. So all of your points would lie on the regression line, but you'd have a positive correlation. Now, of course, you're highly unlikely to get perfect correlations, be they positive or negative. So what's more likely is you might have something like this. Let's say there's your regression line, your line of best fit, and you have the points roughly following it, maybe some lie on it, maybe something like that. That might be something a bit more like this, R equals -0.6 perhaps, so they're quite close to the line. And then maybe, let's take this one. Let's make them a bit closer this time, but still not perfect. I mean, that's pretty good. So that might be something like R equals 0.8 or 0.9 perhaps. And then if you've got no correlation, R is 0. So no correlation, remember we're talking about a linear correlation. Even if I forget to say the word linear, I'm always meaning linear now. So a no correlation, no linear correlation might look something like that. All over the place, but it also might look something like this. There's some kind of relationship going on there. It seems to follow a circle, but it's not a linear relationship. So we can't apply the product moment correlation coefficient, and R would come out as 0 for that because R only tests for a linear relationship. Now, there is a lovely complicated calculation for finding this, and you'll be pleased to know you don't need to know how it's calculated. Your calculator does all that for you. So I'm going to show you how to use your calculator to find the PMCC on example 2. Now, if you could have a look at example 2 in your book, please. We're given some data from the large data set. We're given the daily mean wind speed in knots and the daily maximum gust in knots. And those are recorded for 10 days in September in Herne in 1987. So you've got a table in your book there of all the values, and you'll notice in the gust row, 2 of the values say NA, which of course is not applicable. And the question A asks us, what does that mean? Why does it say NA? Well, the reason it says NA is just because the data is not available on those days. We don't know why. It might be that the instruments they were using didn't work those days, or some other reason. I can't think off the top of my head. I'm sure you can think of a reason why you might not have data on those days. Point is, we didn't have data on those days. Part B, we're asked to find the product moment correlation coefficient, the PMCC, for the remaining 8 days. So we're going to use our calculator to do this. So this is how we do it. You'll remember from last year doing single variable calcs on the statistics menu. So we're going to go back to the statistics menu, number 6 here. And instead of single variable, we're actually looking for linear correlation. So we pick number 2, which is our straight line. And you've got 2 rows or 2 columns here for X and Y. So we're going to put our wind speed, W, in the book and the X column. So let's enter those. 4, 4, 8, 7, 12, 12, 3, 4, 7 and 10. Now we are going to enter in the Y column our gust, which is the G row in your table in the book. 13, 12, 19, 23, 33, 37, 10, but then we get to the 2 NAs. So the next 2 values don't have anything associated with them. So we actually need to come across here and delete those. We can't include them. We've got to clean the data of them because they're no use to us. So the last one we're going to do is 23 from the last column. So we've got our data, and you'll remember from last year that you then do your calculations on the data using the option button. So we press option. There's a couple of things that are interesting to us. Number 3, we're not going to use in this chapter, but I just want to show you quickly, because number 3 is the one you're used to using for single variable calcs. And all it does here is it gives us all the stats you're used to seeing, but for X and Y. So you can see the mean of the X value. So that's the mean wind speed. You can see the standard deviation of the wind speeds. And if you come down, you can now see the mean of the Y values, Y bar there. So that's the mean of the gusts. And a bit further down, we've got the standard deviation of the gusts. So we've got all sorts of things there that are useful to us, but not specifically for this chapter. So if we go back to option, and now choose number 4, regression calculations. So we can see that we have y equals a plus bx, so we're talking about a linear straight line regression model. It tells us the value of a, which is our y-intercept of the line. Now in context of the question, a there would be the value of y when x is 0. So that would be the value of the gust when the wind speed is 0. Then b would be the gradient of the line. So that means for every increase of 1 in x, the increase in y is 2.59. So for every increase of 1 knot in the wind speed, the increase in the gust in knots is 2.59. But the one we're interested in here specifically now is R. So this is our PMCC. This is 0.9533. And we're generally going to give these values to 4 decimal places unless we're asked to do otherwise. So what does that mean? That means that the correlation is really strong. And it's positive. So we have a strong positive correlation. And if you were to draw the scatter graph for this and draw on the regression line, you would see that all of the values are very close to the regression line, and the regression line is very clearly positive. So let's have a look at part C. It says, with reference to your answer here, comment on the suitability of a linear regression model. Well, this here is very close to 1. So that means we've clearly got a linear correlation going on, and a pretty strong one. So a linear regression model is going to be good. If this value had come out closer to 0, we'd be more inclined to say, oh, maybe it's not a linear regression, maybe there's something else going on here, or maybe there's no correlation at all. But this is showing us, yeah, this is very good. So what we can say from this is R is close to 1. So that implies that there is a strong positive linear, make sure you get that word in, correlation. So let's answer the actual question. It says comment on the suitability of a linear regression model. So we say a linear regression model is suitable. Could say it's very suitable here because there's clearly a linear relationship going on. Okay, that's it. Have a go at exercise 1B.